In today's lecture, we are going to cover some linear operators. Okay, why we are interested in this? Because see, in quantum mechanics, uh, mostly the operators, okay, are represented by matrices, specifically Hermitian matrices, and the operators are linear. And we have already studied about linear transformations. Okay, so I told you in the lecture of linear transformation itself that linear transformations can be also interchangeably written as linear operators. Okay, so the properties would remain the same. The answer is that I'm going to use now a few words, a few terms that are more applicable, or you will see more, quite more occurring in physics. Okay, so let me see that if people are joining in, then we'll start. Okay, so let us recap what we have done so far in this journey of linear transformation, because it has been a week or 2 weeks since we are doing this. I urge you that see what is going to happen. I know that these things you might feel that okay, these are not the things that really meant to be discussed. But see, if you understand all these things, then it will be a good thing for you. Okay, it will be a very good thing for you. Okay, so we've gone through some linear transformations in our previous classes. Okay, just let me this. Okay, so linear transformations. See, if I am saying that there is a vector space U and there is a vector space V, then the function t defined from U to V is called a linear transformation. Is called a linear transformation. Is called as a linear transformation if it satisfies two of these properties. Okay, I told you in the very first lecture, just recapping you, that is I'm combining these two topics, and let's say this is u1 plus alpha to u2, it is equals to alpha 1 tu1 plus alpha 2 tu2, where alpha 1 and alpha 2 belongs to field f over which your vector spaces are defined. Please remember. Okay, so this is how you define your linear transformation. We have seen many linear transformation. For example, zero transformation is one. Okay, for example, we have seen projection transformation. Okay, we have seen reflection transformation in our classes, previous classes. Okay, all these things we have seen, and further we have seen what is range space and kernel. Okay, kernel, or you can say null space. Okay, hey, just give me a minute. Okay, sorry. So what is a, we have seen what is range space, and we have seen what is kernel. So this is another definition that we have seen already. And see, the range of a transformation T, that is linear transformation, range of T denoted by RT is the set Tx for all x belongs to U. So you take all the elements from the set U, you plug them into this transformation, you get this image set. So this image set of T under U is called as the linear, is called as a range set. Okay, so I hope this is clear to you. Okay, I don't know what is wrong with it. Okay, now this is fine. See, so now, okay, so now let us come to kernel. What is kernel? So kernel of a linear transformation okay, kernel of a linear transformation gives us all those you can say, gives us all those, what you can say, all those x belongs to U such that Tx becomes 0. So always remember that kernel T is a subset of U, and range T is a subset of V. If we are describing linear transformation from U to V, then always remember that kernel T is a subset of U and range of T is a subset of V. It is a subset of V. I hope it is clear now. Okay. With all these things said and done, we also did something called as rank and nullity. What is rank? Rank is nothing but it is equal to the dimensions. You can say the dimension of range set. So I'll say the dimension of range set is called as rank, and what is nullity? It is called as the dimension of the kernel. So this is how you define your rank and nullity. And one of the theorems that we have just written in the previous section, probably that's not of much use in physics, but okay, but one needs to remember that rank of T plus nullity of T is equals to n. And what is n? So I told you that if T is a linear transformation from U to V and the dimension of U is equal to n, then always remember that rank of T plus nullity is equals to n. Rank of T plus nullity equals to n. Okay, let us take one example to understand what is the utility of the same. Okay, what is the utility of the same? So let us do a question. So question says that let T be a transformation from R cube to R, and you can say be a map from R cube to R such that what tx x comma y comma z is going to do, it is going to write x plus y plus z. So after all, what is happening? You are giving three different values to real numbers, that is from R cube you are getting an input, and output you are getting in R, that is one single output, that is R you will be getting. Okay, just give me a minute, let me see if people have joined. Okay, just let me see. Okay, so I hope it is okay. This is fine. So this is one of the linear transformation, and we want to know what is the nullity of T. We want to know what is the nullity of T. Now, in order to find nullity of T, one needs to see that what all values of x, y, z, if I place, I'll get a 0 for that. Okay, and that particular space, the dimension of that particular space defines you the nullity, right? So the dimension of this kernel of T would determine the nullity, right? So one needs to see this is obviously slightly difficult to assess, so I'll write this is slightly difficult to assess. So what I'll use this rank nullity theorem. I'll use this, rank nullity theorem. I'll use this rank nullity theorem. Okay, let us see how. One thing is very much clear that what should I say? Okay, one thing is very much clear that we are talking of R cube here. So one thing is clear that what is the instead of U, what you have R cube here, and instead of V you have this R here. Okay, and if T was defined from U to V, then we remember that rank nullity theorem says that rank of T plus nullity of T must give you the dimension of U, which is n, and here it is 3. So I would write the what should I write? Dimension of range set plus dimension of null set, or you can say null space, or you can say kernel, which eventually is nothing but it is equals to nullity here, should be equals to 3. Okay, and you remember that what is range? After all, range is coming in R. Range is coming in R. Always remember, see, what does it mean? It means that you are going to supply me the values of x, comma y, comma z. That is, you are going to give me input from R cube, and the output I will get in R. So dimension of R is what? 1. So you can say that nullity of T would be equals to what? Nullity of T, which is dimension of kernel of T, that is equals to 3 minus 1, that is simply 2. Okay, so this theorem will give you the one of the estimates of both of these things. Is that clear? Okay, I can go on with isomorphism and all those things, but I am refraining from going there. Let us first understand something very important, and then we'll enter into some different dimension altogether. See, I need to manipulate with things because see, I cannot go on writing linear algebra for you because that is going to be a very difficult scenario. Now, I'm going to do something. I'm going to write many things now, and much of those things I'm going to write without proofs. Okay, but these are very important things, so please do remember. Okay, now we are going to talk about. Now we are going to talk about the vector spaces of the set of linear operators. So see, having defined linear operators, or you can say having defined linear transformations. Okay, so in this lecture and coming lectures, you're going to see that I'm slowly going and writing now instead of transformation operators. Okay, why operators? Because see, now we are heading into somewhere into operator theory in quantum mechanics. Okay, so understand that having defined linear transformation, now just think, can we not make a set of all linear operators? Can we not make a set of all linear operators? Now question arises that whether it is a vector space or not, what that space would be called, what that space would be called. This is something that we need to address. Okay, so with this thing in mind, I'm writing that let U and B be the vector spaces, over field F. Over field F. Okay, we want to consider the set of all linear transformations, or you can say set of all linear operators, from U to V. Let us denote this set by something that, let's say L. Okay, and this L is denoted by this. Let us denote it by some set. Okay, I'm not denoting by T because then, okay, so I'm denoting by L. Remember, without proof, I'm stating that this particular L U comma V, which represents you the set of all linear operators, happens to be a vector space. Under the operations of vector additions and scalar multiplication, where vector addition is defined as if I'm taking operator S, if I'm taking an operator T, and if I'm doing S plus T from U to V, I can say that if U is an element from U, okay, then I can say that S plus T of U is equal to SU plus TU. This is how you define your vector addition, and there is a scalar multiplication defined, and that scalar multiplication says that let us define a scalar multiplication of from alpha SU is equals to alpha times SU. Okay, so if I'm doing alpha S and operating it over U, it is equal to alpha times SU. If these two properties are defined, that is vector addition is defined. This is how I have defined the vector addition over the set of linear operators, and if I define a scalar multiplication with respect to these two operations, it can be proved that this particular space, that is L of U comma V, which represents the set of all linear operators, this forms a vector space. This forms a vector space. And remember, we've done in the initial class TU is equal to 0. This is called as a zero transformation. So, and we have seen that zero transformation is also a linear transformation. So therefore, this particular thing would exist and all other properties can be verified accordingly. So that is something that I'm leaving upon you now. Okay, understand that this particular space, that is a space, or this particular set, that is a set of all linear operators from U to V, forms a vector space. Okay, this is something that you can do on your own, and I've given you the one of the things that you may get confused. remember that first transformation that we did was zero transformation, and this happens to be a linear transformation. Okay, so this will be contained in this set, the negative of tu will be contained in the set, all other properties can be verified, and these are the vector additions and scalar multiplication according to which like these are this is how your operations are defined. Okay, this is how your operations are defined. Now you see, what about the dimension of this particular space? What do you think the dimension of this particular space would be? What do you think the dimension of this particular space would be? Okay, so what do you think this dimension of this L of u comma v would be? Okay, so let me write here. Let U be a vector space over field F, and let's say the dimension of U be equals to M, and let V be a vector space over field F, and the dimension of V is simply N. Okay, and we've already stated that L U comma V, this is the set of all linear operators. This also forms a vector space over F. This also forms a vector space over F. Now, having said all these things, the dimension of this particular L happens to be M into N. It is equals to M into N. It can be proven very easily, but let's just not go into proofs, just write it. So if the dimension of U is M, dimension of V is N, then the dimension of this the space of all the linear operators is nothing but it is equals to M into N. Okay, so for example, if I want to write something like this, okay, something like this, let's say L of, if I want to write L of r square comma r, okay, r square comma r. So what does it represent? What does it represent? What does it represent? See, it represents set of all linear operators, set of all linear operators from r square to r. It represents the set of all linear operators from r square to r. What do you think the dimension would be? So clearly the dimension of r square is what? Dimension of r square is 2. Dimension of r is what? It is equals to 1. So dimension of L from r square to r would be simply 2. So what does it represent? This particular thing would effectively represent a plane only. Okay, because this is sort of, you can say, you can make an isomorphism. So I'm not going there, but understand, you can say that this is similar to, but this is isomorphic to r square only. So it represents a plane. It represents a plane. Now this brings us to another important thing that is called as the dual space. And I'll give you an example from our own instance also. Okay, and now I'll introduce something called as Ketten-Brown notation after this. Not after this, let me take a few more minutes and then see. Dual space. See, you've seen that U is a vector space over field F. V is a vector space over field F. Okay, now what if I define a vector space a vector space of a set of linear operators from U to V? Instead of this, let me define that V is equal to F. So what am I doing? I am defining a set of linear operators from U to F. What is F? F is the field over which your vector space U and V are defined. Okay, so you remember that U is a vector space over field F, V is also a vector space over field F. So remember this particular where your V is equal to F, where V is equal to simply F. this particular space is called as your dual space. This particular space is called as the dual space of U, and it is usually denoted by U star. So let me write it formally, that let U be a vector space over F, over F. Then the space then the space U, you can say L U comma F, is called as the dual space of F. It is called as the dual space of U, and it is denoted by U star. It is denoted by U star. There comes another definition here, that is of the linear, I think functional, I should say, linear functional. So in particular, if you're defining a, you can say a linear transformation, let's say I'll use word T, from U to F, then this particular linear transformation is called as the linear functional. Example, let us take an example of dot product that we did in previous lecture. That is, if I define from R cube to R a dot product with vector A, which is A1 comma A2 comma A3, if you remember that we have proven that this is a linear transformation. So what is happening here? See, after all, you're going to get this result in R only. And what do you think R cube forms? R cube forms a vector space over R. Okay, so here the field is F, field F is R. So basically we say that R cube forms a vector space over R, right? So effectively understand that that this particular definition falls into definition of a linear functional. Okay, so therefore we can say that this particular dot product is nothing but it is a linear functional on R cube. It is called as a linear functional of R cube. Okay, is that clear? Please let me know in the comment section if that is clear. Then I'll move a little bit further. Otherwise, I'll repeat whatsoever I'm saying right now. Don't get confused by all these terminologies. You eventually you're going to get it. Don't worry. And remember, every vector space has a dual space. Remember that every vector space has a dual space. So remember this particular thing, that every vector space has a dual space. Every vector space has a dual space. Please let me know in the comment section if there is certain doubt. If there's no doubt, then we can move further. And if there are doubts, please let me know. Probably all these things you may not have studied, but so for example, let me give you an example and then we'll see what I want to explain. Let's say we want to explore about column vectors. Okay, if you want to create a space of column vectors, okay, if you want to create a space of column vectors, do you think the row vectors will be there? Do you think row vectors will be there? Let's say if I want to say that the state 1 comma 0 is there and state 0 comma 1 is there in some vector space, do you think that this state would be there? No, not at all, because now you cannot define the vector addition. Now you cannot define the vector addition. Okay, for vector addition, your matrices should be compatible. No? How would you define matrices? How would you define vector addition here? Although we know that this is also vector space, we know this is certainly a vector space, but this will not be contained in this vector space. So if you are making a vector space with column vectors, you cannot expect row vectors to be there. But what is this particular space? So this particular space is called as a dual space. In layman, like in literally the most easier way I'm speaking. Okay, remember that rows and columns cannot be a member of the same vector space, right? And I've already proven that n cross n over field F forms a vector space. If I have not proven, then also understand that set of matrices of order m cross n over field F forms a vector space. So always remember that rows and columns cannot be a member in the same vector space, right? Cannot be there in the same vector space, right? So what does this space? What does this space is called? So this particular space is called as a dual space corresponding to this particular space. So remember that every vector space has a dual space, and here we get a freedom in physics, in particular, to introduce something called as the Dirac notation. And this is supremely important because it simplifies our representation of quantum mechanics. So you'll see that we are going to represent much of the things in Dirac representation and Dirac notation as we go along doing quantum mechanics. And we are going to see, I'm going to teach you this linear algebra, and inside this only I'm going to teach somehow the operators and everything. Okay, so till the postulate things, I'm going to discuss everything in this linear algebra only. Okay, this is my objective. Is that clear or not clear till now? Okay, a few things I'm going to write. So one of the postulate. Remember, I have not yet introduced the postulate, but just for the sake of understanding, remember that quantum mechanics follows a postulatory approach. Okay, and there are certain postulates according to which your entire quantum mechanics is formed. Okay, so the treatment in the quantum mechanics follows some postulates. Okay, and this particular postulates are, you can say, nothing. I'm just going to write. So this why postulatory approach? Just remember. I mean, I'm going to cover all these things later on. But always remember that the quantum mechanics in general is governed by certain postulates, and these postulates are nothing but they are result of the experimental observations that we've got. Okay, so remember these, since postulates itself means that they cannot be derived. They cannot be derived. Okay, so because we have seen certain experimental observation, we tried to. I'm not saying we, means like scientists in 1920s and 25s had tried. So, for example, I keep saying that this quantum mechanics is basically divided into two parts. One is called as a wave mechanics, which results. Which is like initial days of quantum mechanics from the old quantum theory, and Schrodinger is mainly responsible for that old sort of treatment where a differential equation type of treatment is given, and that we are going to see in parallel. Probably in this week we'll start. And another treatment was developed by Werner Heisenberg, which is called as a matrix mechanics. So this has simplified quantum mechanics to a greater extent. Okay, so remember that the postulates are nothing but they are developed from the experimental observation only. Since they cannot be derived, does one-dimensional real vector space has a dual space? Bharat, let me just complete this. I'll answer your question. Okay, I'll answer your question. Okay, so postulates are nothing but they are on the they are nothing but they are experimental observation. They are experimental observation after which we have defined certain postulates, and you cannot determine them accurately or like directly. So what is the work that we are going to create a theory? If that theory becomes coherent to your experimental observation, then it is fine. So one of the theory but what we say is that each quantum mechanical state is defined by a state vector. Each quantum mechanical, you can say the state is defined by something called as a state vector. And most often we'll see that this kind of notation will come. This notation, we'll say that this is a ket notation. So now I'm going to cover this particular thing. Okay, I'm going to cover this particular thing. So first thing that why do you think that, as I told you, that why Dirac notation is necessary in quantum mechanics? It is going to let us formulate our theory in easier and clearer manner. Okay, just give me a minute. Okay. Okay, now there are two concepts regarding this. The concepts, you can say, notation regarding this. So kets, what are kets? Kets are the elements of a vector space. Most often you'll see that we are going to represent our column vectors in form of kets. Okay, not only column vectors, just an example I'm giving you. Okay. Okay. So any state vector, I'm writing here that any state vector, I'm going to come to all these points when we are going to study the postulates also. I'm going to cover postulates in very brief, but remember that. एक minute, just give me a minute. Okay, so every state vector is represented by some ket. Okay, so basically remember that lately I'm going to introduce a term called as Hilbert space. So for that we need to define inner product. So right now I'm not doing that. Remember that every state vector is represented by some ket notation. Okay, and corresponding to this, as I told you that every vector space has a dual space. So there is another you can say that thing that is called as the bra, and these are nothing but these are the elements of the dual space corresponding to the vector space. Okay, remember that for every ket there exists a bra. So there is a one-to-one unique correspondence between the ket and bra. Okay, so remember this thing. Okay, so I guess this is clear or not clear? Okay, and do remember that all these things, if that is clear, I'm going to come on to the doubt of Bharat also, but just for the sake of starting, I'm doing it. So always remember that for every ket there is a bra, and for every bra there is a ket. Okay, and remember that we are talking right now, we are just right now talking about finite dimensions only. Till now we have not covered the infinite dimensions. So there is an important theorem which suggests that A vector space, I'm not talking of infinite dimension, I'm talking of finite dimension. A vector space has the same dimension as that of its dual, if and only if, remember this is if and only if, okay, if and only if it is finite dimensional. So only if it is finite dimensional, then only it will make sense that we can compare the dimensions of uh, vector space and the dimension of the dual space. Okay, so this particular argument has been proven in there is a very standard book of linear algebra which is called as Jacobson. So I'm not going there inside the proof because that will take a lot amount of your time, and probably I've skipped many concepts like isomorphism and all those things. Probably I would cover those topics in group theory, because probably you might have forgotten all those things. So that will create a whole lot of difficulties for you right now. Okay, so it's better that right now let me just recap whatever I have done, and then I'll move further. Okay, then I'll move further. So till now, as I started with linear transformation, and I told you that what is a linear transformation? A linear transformation is a transformation which satisfies this kind of property. Okay, which satisfies this property, that is, which preserves this kind of thing. That is, if t is operated on alpha u1 plus alpha u2, then you're going to get alpha 1 tu1 plus alpha 2 tu2. If this is how your transformation, or this is how your map is functioning, then this particular map is called as a linear map, linear operator, or linear transformation. What is the range space and the kernel? We've seen that range space is nothing that if I take all the elements of U, and if I try to find the image of image of this T under U, all those images, that particular set is called as the range space, and all those X belongs to U for which Tx becomes 0 is called as the kernel. And the special name given to their dimension is rank and nullity, and there is a theorem which says that rank of T plus nullity of T is equal to n. And further we saw a little bit of dual space. I'm going to cover all these things time and again. See, now let us do a few questions just to recap your concepts, and again I'm going to come to the topic. Okay, Ket and Bra, I think you might have got. Just there are theorems. Okay, so there are theorems, you need to understand this thing, that for every Ket there's a Bra, and for every Bra there is a Ket. There is a unique correspondence between Ket and Bra. Understand what is Ket. Ket is nothing but they are the elements of a vector space, and corresponding to this vector space there is a dual space. Remember that every vector space has a dual space, and since this is the case, you can say that corresponding to this vector space there would be a dual space. I have given an example. For example, if I construct a space using column vectors, you cannot expect these row vectors to be contained there, because they will never be compatible for addition and other vector addition. So clearly these will not be contained, but they do form a vector space. So what we can say, that this is the dual space for this. We say that this is the dual space, and you will remember, as I told, that this Ket notation is nothing but this is a column vector. So this is a column vector. Bra vector is what it is. We are going to see that it is the transpose of it, conjugate, complex conjugate transpose, as I'm going to talk a little bit of more detail when I'm going to cover a scalar product and all those things. But for now, just remember that this particular space which contains these row vectors is the dual space corresponding to this particular space. So this here we introduce a handy notation which is called as the Dirac notation. And this is generally to make your lucid, formulate your quantum mechanical theory in a very lucid manner. And this is one thing that you should remember right now. I hope it is clear, and we'll see a few more properties regarding these, but let me just recap for all those who have joined today a few of the things, and then we'll move further. Okay, so as I told you that I'm going to time and again ask you a few questions so that I can see that if you are able to follow or not able to follow. So as I started this particular lecture, I started with linear transformation. Another important result that you can say that can save your life in exam also. See, if there is a linear transformation, always remember that every linear transformation from U to V map a zero vector in U to zero vector in V. I'm repeating it again. So let's say, I'll give you an example. Let's say there is a linear transformation from Rn to Rm. Okay, I have already stated that Rn forms a vector space over R. You remember this? So if this is a vector space, it will contain a zero element. Sorry, zero n I'm writing. And if this is since this is also a vector space, this will also contain a zero element. So this will contain a zero element which is, let's say, 0m, and this contains a zero element which is 0n. Always remember that a linear transformation maps a zero vector in Rn to a zero vector in Rm. This is called a zero vector, or you can say additive identity also, whichever way it suits you, a zero vector in Rm. What do I want to say? I want to say that if T is a linear transformation, then it will always map a zero vector in Rn to a zero vector in Rm. Always remember, always remember. This is one of the important, you can say theorems or result, but this is an important result. And remember, what is 0m? 0m is the additive identity or zero vector in Rn, and what is 0m? It is a additive identity or zero vector in Rm. Okay, so given this, try to think about this particular question. So is the following function from r square to r cube a linear transformation? Do you think that this is a linear transformation? See, T do you think this forms a linear transformation? And I'll come to all of your questions, don't worry. Because see, to formalize a theory, you need to go through some questions so that you'll be able to then understand what am I trying to speak. Otherwise, things will not be that coherent. Just think about this. Do you think that this forms a linear transformation? A few important topics are also that, so we'll do all those topics, don't worry. Do you think that this forms a linear transformation? Just take this example and try to do it, and I'll help you when. Why I have stated start, because I have found that a few new students have joined, so probably they will not get. So transformation, again, let's see. So I told you what is a linear transformation. Linear transformation is one which satisfies all those properties that I told you initially. That is, if I'm saying that T is a linear transformation from U to V, then it must satisfy T alpha 1 U2 plus alpha 2 U2 is equals to T U1, and this should be equals to plus alpha 2 T U2. This is how, if this is the case, then things are, then we can say that this particular T is nothing but this is the linear operator or linear transformation. Okay, now let us start writing a few more things here. So as I told you that every linear transformation maps the zero vector to zero vector. By zero vector I mean, again, please do remember, zero vector means what? Zero vector means an additive identity in U to an additive identity in V. So what is an additive identity in V? So for example, Bharat was asking that whether a one-dimensional real vector space has a dual space. See, whenever you have to see a dual space, please mention what is a field over which you are defining. See, what is dual space? Understand. I'm just giving you a hint to your question. What is a dual space? And I'll come to a few questions, and then probably you will be able to relate to what like you'll be able to formalize this definition of dual space. This is not easy concept. Okay, then there will be something called as bi-dual space. So all these things are very mathematical. Okay, so again, as I told you, this linear algebra is a 2-semester course. It is a 2-semester course. For BSc 1 semester if we take, and for MSc we take 1 semester, so it's almost 2-semester course. And all of this you have to understand in brief. Being a physicist, one cannot go into the theorems and start deriving them, okay, because that is the job of a mathematician. We are here to just exploit a few results of the linear algebra. Okay, so remember what is a dual space, just because I'm addressing a result here, addressing a doubt here. So the student has asked that does one-dimensional real vectors real number space has a dual space? So indeed it will have, because see, always remember that a dual space is what? After all, if U is a vector space over field F, and if I define an operation that is a linear operator from, if I define a set of linear operators, if I define a set of all linear operators, okay, from U to F, this particular space of set of all linear operators from U to F, what is F? It is the field over which this U is defined. This particular space is called as a dual space. And remember, if you are considering a finite dimensional vector space, then the dimension of U and dimension of the vector space of the dual space are equal. These are both equal. Remember, always remember. And there is a theorem which says that every vector space, finite dimensional, will have a dual space. So indeed, from R, which happens to be a linear vector space, there would be a dual space also. There would be a dual space. Now let us come to a point which is every linear transformation maps a zero vector to a zero vector. Now what does that mean? It means that if I am considering Rm, as I told you, and if I am considering Rn, if this zero vector is 0m and here zero vector is 0n, then if T is a linear transformation, then it should map zero vector to a zero vector. So let's say in this example, what is R square? R square represents your Cartesian coordinates, Cartesian plane. So here your 0, 0 should get mapped to 0 only. What is 0? 0 is 0 number 0. Number 0 in R. Okay. So this is one of the requirements. So if one wants to negate that whether this is a linear transformation or not, if one wants to negate that this is not, one wants to negate the statement that this is a linear transformation. If one wants to say that this is not a linear transformation, what may come to your rescue? You can use this particular thing. You can use this particular thing. You can use this particular thing. Is that clear? Okay, so this is R cube, I guess, not R. My mistake. So it should map to 0, 0, 0. Okay, this is a 3-dimensional space. No? From 2 dimension, we are going to 3 dimension. I think I have made mistake. Okay, no, 3 is written. Okay, 3 is written there. Okay, so I want to check that whether a 0 vector is getting mapped to 0. If it is not, then it cannot be a linear transformation. If it is not, then it cannot be a linear transformation. Let us check. So if I want to see where my U 0, 0 gets mapped to. So according to your definition of the question, it is going to get mapped to 0 plus 0, 0 plus 1 and 0. So it is going to get mapped to 0, 1, 0. Indeed, this is not a 0 vector in R cube. This is not a 0 vector in R cube. Remember, every linear transformation maps a 0 vector to a 0 vector. So one of the ways, you don't want to get into this mess. This is a long thing to do. Just see that whether your linear transformation is mapping a 0 vector to a 0 vector. If it is not, then it cannot be a linear operator. It is not a linear operator. So if you define, if this is written this way, if you write this way, that if you're defining a map from 2 dimension to 3 dimensions, and someone asks you that whether this is a linear transformation, no, it is not, because it cannot map a linear. It is not mapping your T 0, 0 to 0, 0 to 0, 0, 0. Had it been a linear transformation, it would have mapped your 0 vector in R square to a 0 vector in R cube. But it is not the case here. So remember, one of the ways to negate an exam is this. One of the ways to negate things in exam is this. Is that clear or not clear? Okay, I hope it is clear. Now I'm going to do a few more questions for you so that you can fix yourself with this particular concept of linear transformation, and then I'm going to come to dual space again. So that now, and in between I have also inserted a little bit of Dirac notation. Okay, right now, and as I told you, I'm going to just do all this time and again. I'm going to use all these things interchangeably so that you are well aware with the concepts in mathematics, and you can draw correspondence in physics also. Okay, you can draw a correspondence in physics also. Is that clear? Okay. Okay. So let us take one example from. I think that would be a good thing to do. Let us take one example from quantum mechanics also. Let us take one of the example from quantum mechanics also, so that at least you draw some sort of similarity. See, in quantum mechanics, you might have, even if you have done it at BSc level also, you might have seen that the momentum in one dimension, let's say in x direction, is represented by a is represented by an operator. I'm not right now saying that linear operator. I'm saying that, let's say, your momentum is being represented by this particular fellow. I'm not even addressing this as a linear operator or operator anything, because right now I have not stated you some postulates. But remember, I guess that most of you have done at least BSc level quantum mechanics, and you're well aware that that whatever classical, you can say, observables, you can say, no, classical observables are represented as operators in quantum mechanics, right? So the, let's say if I'm saying that px is the linear momentum, so corresponding to this is an operator in quantum mechanics, and I want to know that whether this is a linear transformation or not, that is whether it is a linear operator or not, how to go about it. So let's say this is your operator px cap, and we want to know that whether it is a linear, is it linear or not? Question is it linear or not? How to come to this particular conclusion that it is a linear operator or not? See, in order to understand this, I will have to see that if I take two functions, let's say wave function psi1 and plus psi2, and if I multiply it with alpha 1 and let's say alpha 2, what am I going to get? I'm going to get this minus iota h cat would remain as it is, and this alpha 1 would remain. See, derivative operation uh, takes a constant outside, so you'll have this del psi 1 upon del x plus alpha 2 del psi 2 upon del x, which is equivalent to, so what I have done, I have done this p x cap, and I have operated over alpha psi 1 plus alpha 2 psi 2. And what have I got? So if I take this particular thing, I have got alpha 1, and what is this? This is px psi 1, and this is plus alpha 2, and this is px psi 2. So what have I got? I was operating px over alpha 1 psi 1 plus alpha 2 psi 2, and I have got alpha 1 px psi 1 plus alpha 2 px psi 2. So clearly this momentum operator is a linear operator. It is a linear operator here. Although we are going to see that all of these are linear operators. Okay, so our theory of entire theory of this quantum mechanics is based upon all these things. So indeed, this momentum operator is a linear operator. Is that clear? I hope it is quite easy for you. This is something that you've done in your BSc section also. Okay, I guess this is clear. Please keep responding on chat, otherwise I'll not be able to understand what are you getting or what are you not getting. Okay, that's quite clear. So see, having said done all these things, now let us do a few more questions on linear operators so that you'll be able to understand what I intend to develop right now. Okay. Okay, so let me just give you a question, so that would be a good thing to do. Okay, so What do you think integration would do? So I'm writing here. What do you think that integration would do? So uh, let me define it further. Okay, so I'm defining something like let R be a set of real numbers. Okay, let R be a set of real numbers, and what I'm trying to do, I'm trying to define a vector space of all functions. This V is vector space of all functions from R to R, which are continuous. And you know that I have stated in the very first lecture that the set of all continuous functions forms a vector space. Okay, so I hope everybody is quite acquainted with this fact. Otherwise, if you're not, you can check it on your own. That let's say if I have two functions, f1 which is continuous over R and f2 which is again continuous over R. So C, if I'm writing C, it means class of continuous functions. Okay, so if f1 and f2 are belonging to the class of continuous functions, then you know by algebra of continuous functions that you might have studied in your calculus that alpha 1 f1 plus alpha 2 f2 is also a continuous function. So vector addition rules are going to get followed and all those things. And you know that a constant function in particular is also a continuous function. And with that constant function, if I take it as a zero function, that will form an additive identity inside this. And if f is continuous, then minus f is continuous, and all those properties, if you're going to verify on your own, you can verify that the set of all continuous functions forms a vector space. Now let me define a mapping. Let me define a mapping from V to V. What is V? Set of all continuous functions which forms a vector space. V is again a vector space of continuous function. And let's say this mapping T is nothing but integral. So that at least integration. Do you think this is a linear transformation? Does this form a linear transformation? Remember, in mathematics, most often you're going to see I'm going to use this word linear transformation. In physics, the same thing I'm going to use linear operators. Okay, so don't worry about it. Linear operator and linear transformation can be used interchangeably. So don't worry about it. Okay, so basically the underlying structure is the same. So do you think this particular thing forms a linear transformation? Indeed, it does. So let's say what is the way to check? As I checked in this particular, because see, I did a derivative case, so that is why I thought let us do a case of integration. So derivative case I actually explained you using something in quantum mechanics. Now I want to do it using something concretely mathematical, which suggests that okay, if this is your integral, do you think that this forms a linear transformation? This particular mapping, do you think that this forms a linear transformation? Indeed, it does. Let's see how. So what should I do? Let me take two examples. Let me take two functions. Let us take g and b. These are both continuous functions, and they will both belong to this set of vector space set. This is v. Okay. Now, if I try to find what this is going to be, so I know that this is going to be integration from 0 to x, f of t plus b, g of t and dt. Remember, if I'm writing t also, don't worry. Eventually, after getting integrated, and if I place the limit 0 to x, it will become a function of x. Okay. So in order to just not confuse you, otherwise if I write x here, then you would say this is x or this is x. What is happening? So that therefore I have written t here. I can use L as well as use x dash here. Okay. So point is this, that this particular thing is going to get inside this, and there would be an integration from 0 to x. Remember, this is a function of x. This is not a function of t. This entire integration is a function of x. It is not a function of t. You integrate this stuff, you put the limits from 0 to x, eventually you're going to get a function of x. Is that clear? So if I write this way, and this, I know that from integral, basic integral calculus classes of 12th class, I know that I can take this a outside, and what am I left with? I'm left with this, and I'm left with this. And I know that this particular thing, I can write it as a t of fx, and I can write this plus b of t of gx. So clearly you see that this integration also forms a, this particular integral operator is also a linear transformation. It is also a linear transformation. See, in the previous step we have proven a derivative, and we have seen derivative in general also. Derivatives in general also. I hope it is clear. Is that clear? I mean, I just want to ask everyone who's live right now. Do you understand what I say, or do you not understand what I say? If you don't understand, I'll repeat it all over again. Okay. And as I told you, please keep patience. Please keep patience for a week or so. Once you are done with operator theory, I'm saying that we are going to get into quantum mechanics very stealthily. You will not be able to understand that you've actually done a quite amount of quantum mechanics. Okay. While since I'm doing operator theory, this particular portion is an important portion for your exam also. Time and again, people have asked questions from this operator theory. Okay, so in parallel, we are going to start with Schrodinger's equation probably from tomorrow, and I'm going to consider that okay, you know a Schrodinger equation, and then I'm going to formulate that particular thing for one-dimensional potentials. The Schrodinger's first, Schrodinger's equation. So that particular thing I'm going to run in separate section, and this particular operator theory and at least matrix mechanics we are going to run in another different as a different entity, so that you're able to get whatever I'm speaking right now. I hope it is clear till now. Please let me know. Is that fine? Is that not fine? Is that fine or not fine? Okay, good enough. So, okay, now sometimes in exam there may be a question of this way also. See, I want to transform a square into a parallelogram. Okay, let's say I want to transform a square into a parallelogram, and I want you to suggest me a linear transformation. Okay, so you just suggest me a linear transformation which will transform a square into a parallelogram. Okay, let us see. Are you able to do it? Uh, Okay, so what I want to say that I want to see what is a square. Square after all is a two-dimensional object, isn't it? So we can expect that we are in R square. And what is parallelogram? Again, we are in R square. Okay, and we understand that there would be some functional formation which will convert a square into a parallelogram, and we want to address that particular thing. We want to address that particular thing. So let us address what would be the linear transformation that changes a square into a parallelogram. Okay, so for that we want to find what is our objective. We want to find a linear transformation which maps from r square to r square, a square to a parallelogram. Let's say I give you some hint, otherwise it will not be an easy thing for you. Let's say t1 comma 0 goes and gets mapped to 1 comma 1, and t 0 comma 1 gets mapped to let's say minus 1 comma 2, and I'm talking of a square here that would, let's say, I'll make it easy for you, so I'm not going to do this. So this is, let's say, 0 comma 0 here, you have 0 comma 1 here, you have 1 comma 0 here, and you have 1 comma 1 here. So I'm talking of a square with vertices 0 comma 0, 0 comma 1, 1 comma 1, 1 comma 0, with the condition that t1 comma 0 is equals to 1 comma 1 and t 0 comma 1 is equal to minus 1 comma 2. What do you think the structure of t would be which will convert this particular square into a parallelogram? Is that clear or not clear? And if this is it, a TFR person would go in and ask that if this is a square here, then under some transformation which we are going to find, what is the area, like how does area goes on to change? This is something that TFR can ask, and probably they have asked also. I will have to look upon that in the previous year questions, but they have asked such questions in exam. Okay, they have asked such questions in exam. So let us think about it. Okay, let us think about it. So understand that why I have taken 1 comma 0 and 0 comma 1, as I have already stated in previous lecture, that 1 comma 0 and 0 comma 1 are the basis sets, are the basis of R square, are the basis of R square. So this is something that we already know. Okay, so if this is the basis of R square, any xy in R square, any xy in R square can be written as what? Can be written in terms of the basis set. If you remember, we have done all these things. We have done linear span, subspaces, everything. So it can be expressed in form of 1 comma 0 and 0 comma 1. 1 comma 0 and 0 comma 1. Is that clear? Because this is the standard basis of R square. This is the standard basis of R square. In order to express any xy, any arbitrary element in R square, I can express it in form of 1 comma 0 and 0 comma 1. Just remember, whenever you are confused with this, just think xy as xi cap plus yj cap. And what is 1 comma 0? It is I cap. What is 0 comma 1? It is j cap. If you are not right now getting things that way, understand that this you can think of as x I cap plus y j cap. You can think this of as I cap, and you can think this of as j cap. Is that clear? I hope it is clear. So what I am going to do, I am going to write x comma y as simply some linear combination. Let's say some linear combination. Let's say I want to see that what will make my x and y. So what I'll do, I will write it as some scalar, let's say alpha 1, and I'm going to write it as 1 comma 0. And after all, I know what is alpha 1 and alpha 2, don't worry. And what is alpha 2? Alpha 2 will be 0 comma 1. Okay, and I want to find this alpha 1 and alpha 2. And I'm already given a mapping that t x comma y is equals to what? It is alpha 1 t 1 comma 0 plus alpha 2 0 comma 1. And if I want to find t x comma y, this will give me alpha 1, and t 1 comma 0 is what? It is minus 1 comma 2. And what is t 0 comma 1? I think t 0 comma 1 is 1 comma 1, right? So it is 1 comma 1. So I can write that my t x comma y. Okay, I think this is fine or not? I think this is fine. So I think this will form the first coordinate would be, I have made a mistake somewhere, I don't know. This is 2 now. Okay, this is fine. I have made a mistake somewhere or not. This is fine. Okay, so just okay, this is fine. Alpha 1 comma 0 I have written. This is fine. Okay, remember that this alpha 1 is nothing but it is equal to what? X. And what is alpha 2? It is nothing but it is equal to y. Okay, remember this is the case. This is one thing that you should remember. Okay, this is fine. If I apply t on both sides, I'll get alpha 1 t of 1 comma 0 and alpha 2 t of 0 comma 1. This is fine. And what am I going to get? I'm going to get okay, this is something I have made a mistake. This is not minus 1 comma 2. T of 1 comma 0 is 1 comma 1. My mistake. That is why I was struggling to see what I have done. 1 comma 1. And T of 0 comma 1 is minus 1 comma 2. Sorry. Okay. Okay. This is okay. I'm so sorry. Okay, so this is one thing. I'll get alpha 1 minus alpha 2 here, comma. And this is what? I think alpha 1 plus 2 alpha 2. Sorry. This is fine. Okay, and remember, never ever mess up with the order. This is something that I've done here. Never ever mess up with the order of the basis. So whenever you are addressing a transformation from one basis set to another, always remember that never mess with the order of the basis. I'll write it somewhere also. I probably have forgotten to write this particular ordered basis, but right now just remember. If you do that, then answers are going to be completely messed up. Okay, so don't do that. So I've got t of x comma y as simply alpha 1 minus alpha 2, sorry, and comma alpha 1 plus 2 alpha 2. If you Is that clear or not clear? And what is your alpha 1? So alpha 1 is simply x. What is your alpha 2? It is simply y. So I can write that my linear transformation would be t x comma y is equals to x minus y comma x plus 2y. So this linear transformation, that is x minus y comma x plus 2y, it is going to convert a square into a parallelogram. Let us see how. That is something I have to verify for you. I have to verify for you. So what we were discussing a square of with vertices 0 comma 0 and then 0 comma 1, and you had a 1 comma 1 here, and you had a I think 0 comma 1 comma sorry 1 comma 0 here and 0 comma 1 here. Have I done some mistake somewhere else also? Let me check. Let me check. 1 comma 0, no, this is 0 comma 1, and this is 1 comma 0. Sorry. Okay, so okay, so this was the square. And what is the linear transformation? Linear transformation suggests that if I'm supplying x comma y, I'm going to get x minus y comma x plus 2y. Okay. So where this particular fellow would go. So let us make a two-dimensional space here. Where your 0 comma 0 would go. 0 comma 0 is going to get mapped to 0 comma 0 only, I guess. So it is not a problem at all. Where your 1 comma 0, this is 1 now. So where your 1 comma 0 would get mapped to. 1 comma 0 is going to map to, I think 1 comma 0 only. No, not 1 comma 0. I think it is going to map to 1 comma 1. So let me write, this is your straight line. Here it is 1 comma 1. Is that clear? You can see on it on your own. What is t1 comma 0? T1 comma 0 would be 1 minus 0, which is 1, and 1 plus 2, 0. This, where your t0 comma 1 is going to get mapped. So t0 comma 1 is going to get mapped to minus 1, and then you have this 2 here. So minus 1 comma 2. So where is your minus 1 comma 2 would be? This is your 1. So let me extend this here, and this would be minus 1 somewhere here. And not here exactly. So I will have to draw it all over again. Just give me a minute. I hope it is clear now. I mean, these are some really difficult things for you, but don't worry. Slowly and steadily, everything you're going to get. Achha, this is eraser. I sometimes get confused so much. Okay. Actually, I want to show it geometrically so that you'll be able to understand things better. So let me make a two-dimensional space completely, and this is 1 comma 0. This is, let's say this is 1 comma 0, so you'll get somewhere here 1 comma 1, and this is 1 comma 1. Minus 1 comma 2 would be somewhere here, because minus 1 would be here, but the height is 2, so minus 1 comma 2 would be here somewhere. And then you have, I guess, another one is I'll have to write t of 1 comma 1. So t of 1 comma 1 would be 0 comma 3. It would be 0 comma 3. So somewhere here, somewhere very far away. So there would be t of 0 comma 3. So okay. So it's a very pathetic diagram. Okay, I have to make. So basically, it is going to be this way. It is going to be this way. It is going to be, I think. Okay, I'll have to see what all are the equal sides first. Okay, so okay, I'll make it to a little more precision now. So your square goes on to the vertices of the square are getting mapped this way. Okay, this is how it is going to get mapped. So I'm going to write it somewhere. So let me write it properly now. Okay, so this is uh, your x-axis. This is your x-axis. This is your y-axis. 0 comma 3 would be somewhere here. Okay, and if I'm writing 0 comma 2 here, so I'll write this is minus 1 comma 2. So minus 1 comma 2 is, if let's say this is your 1, so almost this distance I'll make here. So 1 comma 1 would lie somewhere here. So 1 comma 1 lies here, and if 1 comma 1 lies here, and there is a side minus 1 comma 2, so minus 1 comma 2 would lie somewhere here. Okay, I'll see that what's happening, and 0 comma 0 is here, don't worry. Okay, 0 comma 0 is here. So we'll have to see how to make a parallelogram out of it. Okay, let us first check the sides. So I'll write here the square with sides, uh, with sides. Okay, that is what is the mistake. So why I'm mapping it here again and again. See, 0 comma 3 would be somewhere there. Okay, so this is how uh, some sort of parallelogram. Okay, this is a mistake. Thanks, Bharat, for suggesting me what I was doing wrong. So 3 comma 0 nahi hai, 0 comma 3. It is 0 comma 3. Okay, so 0 comma 3 is here. So now you see this particular square has got mapped to a parallelogram, and for parallelogram you need to see what are the sides. Are they equal? If they're equal, then this is a square only. So I think this is quite easy to see that this side would be root over 1 ka square plus 3 minus 1 ka square, which is I'll write it here 3, and this is how it is. This would be what? This would be, I think, root over 5. And this side, this is 2 minus 0. This is again root over 5. This is again root over 2, and this is again root over 2. So clearly, this particular square with all sides 1, this particular square with all sides 1 has got mapped to a parallelogram. Has got mapped to a parallelogram. Has got mapped to a parallelogram. Okay, what do you think the area would be? So the area would be, if you remember, that if there's a parallelogram, so here area is what? Here area is 1. Is that clear or not clear? Is there anything that people are not getting or something? Except Bharat, nobody is commenting, so I don't know. Is that clear or not? Please let me know. Is that clear or not clear? I don't know. Yes, okay, good. So you see that area, you can find area from area for this. You know, the parallelogram area is what? So if you have given a parallelogram area, uh, let's say this is your parallelogram, then you know that the area of the parallelogram is given by the cross product. If you remember, A cross B modulus. So this will give you the area of parallelogram, and here you know that this area of square is 1. You can verify on your own that this will transform into some different area altogether. So this area of parallelogram, I'm leaving it for you as an exercise. You just need to do is you need to find A cross B and take a magnitude of it. I hope this is something that you know. This is like something that you know already. Okay, from a vector algebra class. So this is something that I feel that you'll be able to do. So same question, almost similar question has been asked in TFR exam. Almost similar question has been asked in TFR exam. Okay, so people keep wondering that where it is coming from. It is coming from linear transformation. Is that clear or not clear? And sorry for this mistake. I don't know why I'm making a mistake. 0 comma 3 would be on the y-axis. It is 3 comma 0. Therefore I was not able to make a parallelogram out of it. Is that clear or not? Okay, so let me go a little bit further and see that a few more questions, so that again things will get into your head. Okay, okay. So just let me give you a question. I think this was asked in TFR. Just let me wait for a minute. find it somewhere. If I don't find, meanwhile, I'll give you another question. Meanwhile, I'll give you another question. Okay. No, isomorphism you don't know. So okay, I'll stuck to an easy question. Otherwise, you'll not be able to get. Okay. Okay. I'll give you another question. Okay. Be easy. That it is easy. It is easy. Isomorphism I have not taught you, right? So I cannot give you a question from isomorphism right now. Okay, so this is fine. This is fine, I guess. Okay, so all these things having said and done, now let us do questions on. I think that would be a better thing to do. Linear, sorry, this thing, dual space. Okay, let me see if there are some questions that can help you with this particular linear transformation. I've actually wanted to see one question on TFR. Actually, I've skipped that question somewhere. That was question. Okay, chalo, let me try. You try this question meanwhile. I want to find the TFR question. But okay, so let me define a map from 2 dimension to 3 dimensions. That is, if I am saying that T is T of A comma B, I'm mapping it to A plus B, comma A minus B, comma B. Okay, and let's say this T is a linear transformation. This T is a linear transformation. Okay, this T is a linear transformation. And I want to find what is the range for this. I want to find what is the range. I want to find what is the range. Okay, remember that for R square, always remember that for R square, the basis sets are 1 comma 0 and 0 comma 1. And these are ordered basis. Ordered basis means what? X comes first and that Y comes later. This is the ordered basis. Okay, we want to find the range. We want to find the range at first. Okay, so by definition we know that what is happening, every point a comma b gets transformed to a plus b comma a minus b and comma b. Okay, this is how it is going to be. So what do you think your 1 comma 0 is going to get mapped to? 1 comma 0 is going to get mapped to 1 plus 0 comma 1 minus 0 and comma I think 0. So it would be mapped to 1 comma 1 comma 1, and your t of 0 comma 1 is going to map to, it is going to map to I think 0 plus 1 comma 0 minus 1, and then you have this 1. It is going to get mapped to 1 minus 1 comma 1. We know that this r square generates, this r square would generate this particular thing, 1 comma 0 and 0 comma 1 generates the entire r square. This is why it is called as a basis. This is what it is going to generate the basis. See, what is this? This is the basis set for the this is the basis set for the image set. This is the basis set for image set. So this will, I'll write, this will generate, this will generate your range of t. This will generate the range of t. So basically what is happening, this is your ordered basis here, this is ordered basis here. This will generate the range of t, isn't it? Yes or no? Please let me know. Is that clear or not clear? See what is happening. You know that 1 comma 0 and 0 comma 1 are the ordered basis for r square. They are going to generate the entire r square. I have mapped these t under this transformation. So these particular things are going to map, these particular basis sets are going to generate your range. Are going to generate your range. Is that clear or not clear? Please let me know. If that is a problem, I'll reiterate whatever I've said. Okay, I'll teach you. I think probably I've forgotten to teach you, but remember that this will generate your range of t. I think that's a better thing to do. This will generate your range of t. Is that clear? And if this generates your range of t, then what will happen? I can say that I can write anything in the form of linear combination of these two vectors. I can write anything in the form of linear combination of these two vectors, that is 1 comma 1 comma 0 and 1 comma minus 1 comma 1. So I'll take two scalars. Let's say these are your scalars. Let alpha and beta be two scalars, and I want to define a linear span out of it. So what will the linear span would be? Alpha 1 comma 1 comma 0, and then there would be beta 1 comma minus 1 comma 1. If they are the basis sets in RT, if they are the basis sets in RT, then what will happen? I know that they are going to be orthogonal, that they are going to be both orthogonal. That is, if I say that alpha 1 comma 1 comma 0 and beta 1 comma minus 1 comma 1, if these are forming the basis, then, and if I equate to 0 comma 0, I can say that alpha should come out as 0 and beta should come out as 0. Let us see. Let us see whether this happens or not. Okay, let us see whether this happens or not. So according to this, alpha plus beta is here, alpha minus beta is here, and beta is here, and it is equals to 0 comma 0 comma 0, which gives you what? It gives you beta equal to 0, and if beta equal to 0, alpha equal to 0. So clearly these two, 1 comma 1 comma 0 and 1 comma minus 1 comma 1 are basis sets. They are basis of your range of the linear transformation. Is that clear till now? Is that clear or not clear? Yes. No, no, Bharat, that was from TFR physics only. So that is why I was teaching. This particular question has been asked almost similar. Actually, that is why I was trying to find that question, but I'll do that tomorrow. I'll do the exact TFR question tomorrow. Okay, this is something similar to that. Okay, so remember that not TFR maths, not TFR maths, TFR physics only. Okay, so this has been made clear. Now, what do you think the dimension of range set would be? So clearly, the range contains the bases. Is how many bases are there? 2. So dimension of the range set would be 2. The dimension of the range set would be 2. People get confused. They think that okay, this is a 3-dimensional thing, so probably the range would be 3. No. Remember, what was range? What was dimension? So dimension is the number of independent, coordinates. You can say number of independent. You can say number. There are 2 elements in the basis. So dimension of the range space would be what? 2. Is that clear or not clear? What do you think the nullity of T would be? What do you think the nullity of T would be? What do you think the nullity of T would be? So see, understand, I have already stated that if you are defining a linear transformation from U to V, where U and V are vector spaces over field F, then dimension, then rank plus nullity is equal to n. If you remember, if I am defining a linear transformation T from U comma V, then rank of T plus nullity of T is equal to n. And what is n? N is the dimension of the field F. N is the dimension of field F. Okay. So after all, if you remember, we defined a linear transformation from R square to R cube. What is R square? Remember, R square is a vector space over R. So this field here is F, and R cube also forms a vector space over R. So this is from field F. Okay, probably I have actually forgotten to tell you that ordered basis concept. Na? So right now just think this way. Actually, I don't know. I have skipped a topic. So I'll do that topic tomorrow. That is the matrix of linear transformation. Otherwise, you'll not be able to get what am I doing. Actually, I'm mapping ordered basis to ordered basis. So ordered basis as a concept comes in matrix of linear transformation. So actually, I skipped a topic. Okay, I'll do it tomorrow for you. Just do this question for today. So this is from R square. R square is a vector space over R. R cube is also vector space over R. This is a field entry here. So you know that. So if I just write this way, dimension of not this n is dimension of u, this n is dimension of u, remember. So if I go back and let you know what was rank nullity theorem. So if you know the rank nullity theorem was here, I somewhere explained this here. If you see that okay, if you see that okay, okay, so here u is what, here u was r cube, if you remember. So this n here is what we write now. If you remember that this is dimension, this is what, rank of t plus nullity of t is n. N is what, it is dimension of u, it is not dimension of field f, sorry. So it is dimension of u. So if I write it here, I want to find the nullity of t. What is t? T is defined as t of a comma b is defined as a plus b comma a minus b comma b. T, I have defined that this is a linear transformation. I have seen that if I take ordered basis in R square, that is 1 comma 0, it gets mapped to 1 comma 1 comma 0, and 0 comma 1 gets mapped to 1 comma minus 1 comma 1. Indeed, they form a linear independent set of vectors. These are the basis set in the range. Remember that what is this? 1 comma 0 is getting mapped now. So basically these are in the range set. These are in the range set. So range set can be spanned by 1 comma 1 comma 0 and 1 comma minus 1 comma 1. Okay. Since they can be spanned by these two fellows, that is 1 comma 1 comma 0 and nullity can be 1. Nullity can be 0. Don't worry. So these two things are going to be the dimensions. So if I want to find the dimension of my range set, the dimension of my range set would be 2. And what would be the nullity of t in that case? So Bharat is right, nullity would be 0. See how? I know that dimension of range set is 2. I want to find the dimension of dimension of the kernel of t, which is nothing but is the nullity. So if you remember, rank was what? Rank is nothing but it is equal to dimension of the range space, which is 2. Nullity we don't know, but we know what is your u. U is this, v is this. So dimension of u is 2. We don't know about nullity. So dimension of u is 2. So clearly I can say that nullity of this particular transformation t would be 0. Okay. Nullity of this particular transformation would be 0. Are you getting my point? And remember, what is the 0? What is the 0? Remember, this particular 0, what is nullity? I think this is, too much for you, but I'm so sorry. I'll repeat this tomorrow all over again because I think I forgot one topic to be taught. That is called as the linear transformation. I forgot that topic. Okay. So what is nullity? Nullity are all those points which belong to R square such that your Tx becomes 0, isn't it? And if it is coming out as 0, this is not single 0. This is what? This is 0 comma 0. Remember, the dimension is R square here. So your nullity T, which is nothing but the null space. If you remember, I have told you that this particular null space forms what? This forms a vector space. I told you that singleton 0 also forms a null space. Here, the nullity will contain only this point, 0 comma 0. Is that clear or not clear? So null space would contain only this point, 0 comma 0. I hope this is too much for today. If you are not getting it, I'll repeat all these things tomorrow. I think there was a skip. I actually skipped a topic. I forgot to teach you that topic of ordered basis, but I hope this is clear. Is that clear or not clear? Is that clear or not clear? So I'll repeat most of the things tomorrow again. I hope to meet you tomorrow. We are taking dimension of range space equal to dimension of U. Right. See, after all, see range. No, we are taking the dimension of range space equal to dimension of U. No. See, again, come back to the question. See, again, I'll explain you the question. The question was, we had this transformation T A comma B to T, what was that? I think A plus B somewhere. If I get the question, where was the question? Okay, the question was A plus B here, A minus B here, and B here, right? So you're mapping from R square to R cube, right? So dimension of range plus dimension of kernel is equal to what? It is equals to dimension of U. So this is U, this is V. So dimension of U is what? 2. Dimension of range, exactly, you know that we had these two vectors, right? 1 comma 1 comma 1, and other one was what? 1 comma minus 1 comma 0, I guess, if I'm not wrong. 1 comma 1 comma 0 and 1 comma minus 1 comma 1. Okay, so 1 comma 1 comma 0. Another one was 1 comma minus 1 comma, what was that? 1. Okay, so these two are the basis. These two are the basis of the range. So what would be the dimension of range? Dimension of range would be 2. After all, what is, see, remember, what is dimension? If you've forgotten, what is dimension? Dimension is nothing, number of elements in the basis set. So the range set can be spanned using these two linearly independent vectors, right? So I can say that this would be 2. So what is dimension of kernel of T? This is nothing but this nullity of T. So this would get cancelled, so your nullity is 0. 0 means what? What is nullity? Nullity is the dimension of the kernel T. So this is it. Now if I say what is null space, so null space are all those elements which have made Tx equal to 0. So if it is 0, so what does it mean? It means it is a 0 space. Null space is simply a 0 space. And this trivial 0 space is nothing but 0 comma 0. And why I'm writing 0 comma 0 and not writing 0? Because see, after all, the null space C, it should come from R square, right? Is that clear? Okay, clear. So I hope I have gone a little bit rigorous, but if you are a physics student and if you really want to cover anything, this is one thing that you should look at. I mean, even if you're not getting things, just find a way ahead. That see in question, if some sort of transformation is given to you, think about how you can construct a functional relationship between the two. And in exam, most often, at least in TFR, people have asked this kind of question, that how does the area transform under some linear transformation. So this is one area that needs to be taken care of. Fine, you can skip this particular discussion if you are not getting the right last one, because this is more sort of mathematical. Nobody is going to ask you nullity in general. But overall, please remember that from tomorrow onwards, we are going to get in slightly into quantum mechanics, and a few more topics like inner product space I'm going to introduce. That will help me to digress more on your into postulates and everything. So probably from tomorrow we are going to get into quantum mechanics, that is more into operator theory. So please keep attention from tomorrow onwards. Okay. If you're not following certain things, don't lose patience. I mean, more of these things are mathematical, but do remember the properties. Like, let's say if I'm saying linear transformation, what all properties classify linear transformation? In mathematics, in physics, nobody is going to ask you what is kernel and range space. This is something that is completely out of box. Okay, nobody is going to ask you. But still, if you have certain knowledge, there is nothing wrong about it. There is nothing wrong about it. Okay, but overall, please do remember what are linear transformation. Please do remember what is a vector space. Please do remember what is a subspace. Okay, these concepts may be asked in your examination. So vector space 1, null space 2, dimension and basis 3, and fourth linear transformation. And fifth we are going to do tomorrow, which is inner product space. So all these things that I've talked in order, please pay focus. Please pay focus. Even if you're not able to follow more mathematics question, fine. I'm not bothered about that, but you should be at least having an understanding of whatever I'm saying. if you have an understanding, you will be able to draw parallels with quantum mechanics. So I hope to meet you tomorrow. Today was a short session. Tomorrow we'll have the usual 2 hour or plus 2 plus hour session. So please keep that in mind, and we are going to continue this particular lecture tomorrow as well. So I hope to meet you tomorrow. Till then, take care. Bye bye.